Hello, once again. So now we're presented with a problem about graphs, and really the one of the most important elements of the study of graphs is to determine when is that they are really identical. In other words, that we are not really confused of their difference only because we are unable to draw them in a specific way. So for that, we have introduced the concept of isomorphism. So we would say that two graphs are isomorphic if there is a bijection between the set of vertices of those two graphs, such that for every two that form an edge, they will form an edge also in the image. Well, that's kind of shaky, or maybe there's a little bit of confusion under this one, but it would say that if U and V form an edge, then also F of U and F of V will form an edge in the other corresponding graph. So, but that's not the only thing that we should come into our attention. We would say that an invariant is a property that isomorphic graphs share. For example, they should have the same number of vertices. Why is that? Well, because there's a bijection between the collection of the two vertices. They should have the same number of edges. Well, why? Well, because there is an edge in one exactly, and exactly when there is an edge in the other one. They should have the same number of vertices with a fixed degree. Why? Because the degree should be preserved, as that is just a property associated with adjacent vertices. And well, they propagate, there should be the same number of subgraphs of a fixed form, for example, cycles or trees or complete bipartite graphs. I mean, now, really, that's what I have, dot, dot, dot. There could be many, right? But now let's put it down to earth, right? How is that we should check whether two graphs are isomorphic or not? Well, to check that they're isomorphic, we will have to come up with the function itself, right? So imagine, right, that I have not labeled any of this. All that I have to do is to make a labeling that will create the same graph here as the one that we get from here, but only the information, right? So what about the following? On this one, I will place 1, 2, 3, 4, and 5. And then from this one, I will get 1, 2, 3, 4, and 5. Now, I'm going to extract the information that I get from this picture, and it should be exactly the same one that I get from this picture. Look, if I look at this one, what I have is that the set of vertices here corresponds to 1, 2, 3, 4, and 5. And the set of edges, well, let's see, there is 1 and 2, that's one edge. There's also 2 with 3. There is also 3 with 4. There is also 4 with 5. And we also have 5 with 1. Okay, so with these two components in here, we construct this graph. Okay, that's information that we get. What about the things that we get from this one? Well, from this one, we get that the set of vertices is 1, 2, 3, 4. What about the set of edges? Well, what about the ones that are adjacent to 1? So we'll have 1 and 2. I also have 1 and 5, and that exhausts those that are adjacent to 1 or that are associated with 1. What about the ones that are associated with 2? So I have 2 with 3. I have 2 with 1, but that's already counted here, so I'm not going to just duplicate it there. I have, what else? 2 with 3, which is listed. I have, well, I have to move. So 3 with 2 is already listed, is here. 3 with 4, well, that's a new one that I haven't listed. And I think that's it. in those terms. What about those that are associated with 4? So 4 is adjacent to 3 and is adjacent to 5. That of 3 is already listed, so that one. What else? You may say, well, what about those that are associated with 5? Well, 5 is adjacent to 4 and to 1, but that's already listed, so that finishes it. But then you may say, oh, look, as collections, well, this B is exactly the same as this one. If you want to put a prime here, it doesn't matter, right? Just to signify their apparent difference. But you see, I have the vertices here, which are present here. And I have the edges here, but all of them are present here. Look, 1, 2, 1, 2, 5, 1, 1, 5, because the order in which I write the elements of a set is irrelevant. 2, 3, 2, 3, 3, 4, 3, 4, 4, 5, 4, 5. So what is that we have done here? Well, essentially, we have constructed an isomorphism between these two graphs. So the vertex that we have here is going to be sent to this one. The vertex that we have here is going to be sent to this one. The vertex that we have here is going to be sent to this one. The vertex that we have here is going to be sent to that one. And this vertex is going to be sent here, while preserving all the adjacency associated with them. Now, to demonstrate that they are isomorphic, we will have to make such a construction, such an explicit map. There's no way around it. But what about to demonstrate that they are not? Well, one of the usual things to do is to select one of the invariants of the plenty that are available and see if one of them is not, well, it's actually violated, it's not preserved. Well, look. In this case, I'm going to use this one. Number of vertices with a fixed degree. Look, in this graph, if I signify this one, this vertex, this is the only vertex of degree 4. Why 4? Because there are 4 vertices adjacent to it. And then I ask, well, what about vertices of degree 4 in this graph? Well, there's none of them. What does that mean? That means that it's impossible for these two graphs to be isomorphic, because if they were isomorphic, well, this vertex should be sent to one of these ones while preserving the adjacency. In other words, once we make the map, there should be one vertex of degree 4 here, but there's no such a thing. So what is the assumption that is erroneous? That there is an isomorphism. What does that mean? That these two graphs are not isomorphic. So in a summary, if we were to make the comparison, how would you determine whether two graphs are isomorphic or not? Well, to show that they're isomorphic, you actually have to make the construction. To show that they are not isomorphic, well, one thing that you can do is to demonstrate that they violate one of the isomorphism invariants. Okay? So let me know if you'd like to get more examples like this and problems of this kind in a subsequent video. So take care, subscribe, see you around. Bye-bye.